Hello, Drillbotics Committee. We are the virtual rig team from the University of Stavanger, and we are going to present our work for the 2021-2022 Drillbotics Competition Edition. The table of contents of this presentation will be the following, starting with a brief introduction to every team member of Drillbotics UiS team. Then we will introduce a simulators overview and a GUI plus backend for its integration. Afterwards, we will elaborate on the models integrated in our virtual rig, and a flowchart explanation to have a clearer view how everything works in our system. And finally, conclusion and future work for the 2022-2023 edition. We are an amazing team made up of 8 key members, students from different specializations, including petroleum and data science background. Our supervisor is Dan Sui, UiS professor, and in the image attached, we will start mentioning the key members from right to left. We have, first of all, Reinald Villabona Gonzalez, computational engineering student from first year, as well as Akber Hussain, first year computer science student. The rest of the members are about to graduate and are second year students, starting with Ali Tahir, computational engineering student, Muhammad Usama, computational engineering student as well, and Emre Gokmen, computational engineering student. Finally, we have petroleum engineering student Alina Shashel, reservoir engineering specialization, and me, Miguel Fernandez Berrocal, drilling engineering student. The main page of the user-friendly website for UiS Virtual Rig Drillbotics team can show an overview of the different features that our simulator can present to the user, starting with the optimal well path after importing a CSV file of the points our trajectory should go through, as well as after getting inputs from the user in terms of weight on beat and RPM. We can get a depth-based data results visualization as well as time-based data results visualization, which we will elaborate a little bit more in the next chapter. If you're interested in having a look at our Drillbotics Team A website, you may find attached here the link to access to it.
Hello, so I will be describing a little bit about our graphical user interface. Here you can see for depth-based data view and time-based data view, we have shown some of the plots, and those are listed here. And we are also, for both of the view, we are also taking some inputs for flow rate, RPM, WB, and time difference input. With the slider, we have set up fixed range. You can slide and give the change the value as well, and also we have the option to change the mode, automatic and manual. There you can see the final plot output. We also can, from the drop down, you can select and deselect in the main website view. And also you can see the RSS simulations here as well. And for the overall graphical user interface, we have used HTML5 and CSS3. We also use JavaScript, jQuery, and Bootstrap. And for showing the plot, we have used HighChart, that's a JavaScript framework. Thank you.
The following are the models taken into consideration, starting with top model for torque and drag to measure the contact force between the drill string when it's moving and deformation, for obtaining hook load and surface torque. Another top model would result in calculation of bottom hole pressure. Next, ROP BINGAN calculation based on formation characteristics provided. Nonlinear constraint BINGAN ROP optimization based on constraints such as vibration, buckling, and maximum torque and drag. RSS simulator trajectory control using reinforcement learning. MPD optimization using reinforcement learning too. Finally, data analytics and preprocessing of the output data, and formation classification based on hardness.
In Python, we developed this model using mathematical formulas to estimate accurately the torque and drag that we might experience during the drilling of the deviated proposed well. The inputs of the model is a CSV file with the trajectory of the well, and it has the azimuth, the inclination, the MD, and the TVD data from the well. Also dimensions of the pipe and its density, and the density of the mud that will be used. The outputs of the model are two CSV files with torque and force information, which can be used in forward step of the model. Also the data of the surface torque and the hook load, they will be visualized in the front end.
The bottom hole pressure is estimated using shooting method technique. This technique is the following. At first, we assume that our outlet pressure is, let's say, 1 bar. This is the physical boundary condition that we have to ensure that our model reaches. If a choke is, for example, present, the surface pressure will be different. We start calculating the pressures by the deepest node. With the pressure, we assume P bottom guess and the known inlet mass rates at bottom. This can be set to 0 or to another value. All variables are then found in this node applying conservation laws. For each segment, next node, all the way up to the surface, we calculate the pressures, superficial velocities, phase velocities, and volume fraction moving upwards. We use momentum equation to calculate pressure in next node using hydrostatic pressure and the friction model. The superficial velocities and the other variables are found using the two mass conservation laws combined with the slip ratio. In the end, with some surface rate and a surface outlet pressure, the calculated outlet pressure should be equal to the physical outlet condition, atmospheric, let's say. We can therefore define our bottom well pressure as P calculated surface minus P real surface. The function will be 0 if the correct bottom hole pressure is found. ROP was modeled through Bingham equation, based on formation features presented in the table attached, where for every depth range, we will have a different drillability coefficient, K, based on our simplification that the formation gets harder and harder as indicated by the CCS value for every formation range. The optimization of the ROP presented can not only select the optimal drilling parameters, weight on bit and RPM, and subsequently optimize ROP, but also the constraints suffered during drilling operations. The nonlinear constraint integration approximates our ROP optimization as much as possible to reality. We start with an initialized value of ROP optimization for weight on bit and RPM here, and the final result of our optimized formation-based constraints, which will vary, stretch more, or become narrower, depending on the formation, and this result of ROP optimization will give us the optimized weight on bit and RPM, and subsequently ROP optimized value represented here or along one of these curves. These constraints may represent, for example, orange area surface vibration, red area, top drive, max power, and backward whirl, and blue area, stick slip, and green area, minimum values for weight on bit and RPM for our drilling operations.
RSS simulator trajectory control by reinforcement learning. Optimizing path control by reinforcement learning with varying drilling parameters as an introduction. The objectives in here: seeking the best drillable path the closest to planned well path, optimizing weight on bit and RPM values through hundreds of episodes done by agent, achieving highest ROP while controlling the path, and ultimately help to make efficient, fast and cost-effective drilling by the aid of AI support. Expected deliveries are master science thesis as a reinforcement learning assisted RSS simulator, and also implementation in simulator fall semester 2022. In this slide, there is graphs to show that the parameters effect and showing the variances of ROP values and the changing differences between the PVP and the RSS values, RSS paths. And the first figure is showing that 80 kilonewtons with 100 RPM, and it is perfect matching, but the ROP is very slow. In the second figure, the weight on bit is 200 kilonewton, RPM is 100, and it is diverted from the planned well path. And the last one is same weight on bit, but RPM is increased, and the diversion is so much higher than previous two ones, and the ROP is also higher. This is the flowchart of this work. First, in MATLAB, we will read the survey data and create the planned well path with the shown parameters, and the reinforcement learning toolbox take these parameters and give it to the Python, which consists the RSS function with the previous drilling matrix and weight on bit and RPM values as action. It will change every step weight on bit and RPM values, and it will iterate through the PVP matrix. And as from the calculation, we will get the observations through vertical depth, north and east. Also, we will get some inputs for the reward function. These are tool-face real, tool-face drill, and ROP, radius of ellipse, and dogleg severity. And after calculation in the reward function, we will receive the stepwise reward, and it will turn to reinforcement learning. It will make the hundreds of episodes.
Another application of reinforcement learning in our study is in the process of managed pressure drilling. And the aim of this research is to explore a hybrid control system where a reinforcement learning agent can potentially add value to a control process controlled by a normal PID controller. The objectives of the study are that the reinforcement learning agent suggests or recommends the PID set points, for example, in this case, the desired bottom hole pressure, and also tunes the gains of the PID controller, for example, the KP, KI, and KDs, to improve the dynamic response of the PID controller, and also to improve any the drilling efficiency and avoid any drilling incidents which can cause harm to our drilling process. A similar technique can be used in the optimization of ROP as well, and the reinforcement learning agent will be suggesting weight on bit and RPM in that case. The delivery of this project or this study is in the form of a master's thesis titled Application of Reinforcement Learning in Managed Pressure Drilling, and this will be handed in by the end of this semester. An implementation of this study in the simulator will be done in the next semester, that is the fall semester of 2022. The following diagram shows the schematic or the basic methodology of the uh, process which is employed in this master's thesis. First of all, to the left, our drilling or simulation environment consists of is based on OpenLab simulator, which is maintained by Norse, and this is basically a physics-based simulation. And the purpose of using this is to make a stable training environment for our reinforcement learning agent, where we can run various simulations in different drilling scenarios, so that we can put all the performance of our reinforcement learning agent into numbers, which we call reward in reinforcement learning. And then a reinforcement learning agent suggests the PID suggests the set points to the PID controller, which can be weight on bit, RPM, and the bottom hole pressure in case of MPD, and also, it tries to tune the KP, and KDs of the PID controller at the same time. If this combination of actions taken by the reinforcement learning agent, which are the set points and the tuning parameters, are good, we get a very high positive reward. And if they are not good, we get a negative reward or a lower positive reward. Once the simulation results are fed back into the reinforcement learning agent, the critique tries its best to uh, come up with a policy or suggest a policy which gives the maximum positive reward or a maximum positive reward which is possible in the current drilling scenario, and the actor obviously tries to achieve or reach to that policy. And at the end of the simulation or end of a good number of training episodes, our reinforcement learning agent has reached to a policy where it has recognized which actions gives the maximum or highest reward in which drilling scenarios, and the result is optimized rate of penetration and also the optimized control of MPT.
Data analysis. The purpose of data analysis is to extract useful information from data and later on helping in taking the decision based upon the data analysis. In our case of data analysis, we will first choose our data drilling data file in CSV format for the visualization and analysis on the data. After choosing our file, it will take some time depending on the size of the data file, and later it will visualize all the parameters in data file into formats. First format of visualization of data will be with respect to time, and later second visualization of data will be with respect to depth. During our visualization, we can select a specific parameter by deselecting all the others parameters, and later we can download this data and plot of this specific parameter too. In second part of the data analysis, we are calculating numeric values of average rate of penetration, total time, and total depth too. In the third part of data analysis, we are plotting normal distribution bell graphs of our three specific parameters. One of them is rate of penetration, ROP. Second one is RPM, revolution per minute, and third one is WOB, weight on bit. And if we were to talk about our GUI development, we have used HTML5, CSS3, jQuery, Bootstrap, and JavaScript for JavaScript. And for plotting purposes, we have used JavaScript library HighChart. This library comes with all the tools that we needed to create data visualization. Thank you so much.
Formation hardness is identified by mechanic-specific energy. It has been calculated using downhole torque, weight on beat, RPM, and ROP. Based on a values range of unconfined compressive strength, the hardness is defined. The simulator consists of manual and automated modes. In manual mode, the user can input weight on beat and rate of penetration. There is an automated mode presented on the slide. No user interaction is required, since the simulation is working autonomously. For instance, trajectory, rate of penetration, and subsequently the rest of the parameters are optimized within the model. Backend models include topside trajectory control, formation identification, and ROP optimization models. Software structure. Front end is connected through the API mode to backend module with an access to the database.
For our future work, we may consider to allow to update the trajectory or modify it once the simulation has started. Also, it would be interesting to add bottom hole assembly model development. fluid dynamics, Hutton's transport, temperature for MPV integration in our simulator. And finally, keep enhancing our web-based UI. Thank you very much for your time. We are looking forward to competing next week on the 14th of June. See you there.